Okay, enthalpy. That's kind of a weird word, right? Sounds like maybe you have a lisp. Enthalpy. Enthalpy is the sum of the internal energy and the product of its pressure volume. So if a chemical reaction happens open to the atmosphere, then the pressure will be constant, but the volume can change. And so heat can, energy can evolve both as heat and as work. This isn't the bomb calorimeter where we force the volume to stay the same. Many times we are only interested in the heat. We don't care about the work because it's not useful for anything. And so it's convenient to ignore it. So enthalpy is a way that we've come up with to ignore the work done. Right, so enthalpy has an H. I think H would have been better for heat and E for enthalpy, but again, they did not consult me. Enthalpy has an H in it, if that makes us feel any better. Enthalpy is the internal energy plus the pressure times the volume. That is something that a system has at a given point in time. If we look at the change in enthalpy, this is useful because enthalpy is a state function. It doesn't matter how it got from its initial position to its final position. It only matters the difference. And it's a state function because internal energy is a state function, pressure is a state function, volume is a state function. They don't depend on the path. So if we look at enthalpy change, delta H is the change in internal energy plus pressure times the change in volume. The pressure here is not a change in pressure because the pressure is not changing. So delta E is Q plus W. Here it's Q at constant pressure plus W plus P delta V. So now we have Q at constant pressure plus W minus W, because this is equal to W. And we made the W's go away. W minus W is 0. And so we made delta H is equal to Q at constant pressure. Delta H was Q at constant volume. The change in enthalpy is the heat exchanged at constant pressure. What is the difference between these? Because it's confusing. They seem really similar, right? And they are very similar. They're similar in concept, and they are often similar in value as well. Delta E is a measure of all the energy, heat, and work that get exchanged with the surroundings. Delta H is a measure of only the heat exchanged under constant pressure. So most of the time, we don't need to care about the difference. The only time the difference is significant is when you have reactions that either produce large quantities of gas or consume large quantities of gas, and therefore the change in volume is really big. But most of the time, we don't have to worry about that. Yep.
Is the reason there's not work associated with the enthalpy because there's no change in pressure?
It's because delta E has work in it, and the other part has, let's go back to that. So the change in energy is the Q at constant pressure plus the work done. And the enthalpy here is the internal energy plus the pressure times the volume. Because it is. Kind of. So a lot of these things, I can explain it to you to a certain point, and then you just have to believe me and take more science classes so that you can understand the rest of it. But we defined H as the internal energy plus the pressure times the volume. The change in enthalpy is the change in energy plus the pressure times the change in volume. The pressure is constant. we learned that E is equal to Q plus, well, delta E is equal to Q plus W. And we also learned that W is equal to negative P delta V. So we use this equation to change P delta V into negative W. We use this one to take the delta E into Q plus W, and we end up with Q plus W minus W. And it's kind of cool and disturbing at the same time. It's like this math voodoo that we do with equations. Conceptual problem. Lighters are usually fueled by butane. When 1 mole of butane burns at constant pressure, it produces 2,658 kilojoules of heat and does 3 kilojoules of work. What are the values of delta H and delta E for the combustion of 1 mole of butane? So we don't actually have to do a calculation, but we do have to examine the numbers and what they are. So it produces 2,658 kilojoules of heat. Well, heat is Q, right? If the system, the combustion, is producing this, that means it's going out. Is it positive or negative? It's negative. And it does 3 kilojoules of work. So the work is 3 kilojoules. This is work that it's doing, not that it's having done for it, right? So me doing work is a bummer. It's negative, right? So this is also negative. Delta H and delta E. Well, delta E was Q plus W, and delta H at constant pressure was what? It was just Q at constant pressure. Right, back here. Delta H is equal to Q. We got the W's to cancel each other out. So delta H is equal to Q. Q is this number. So delta H, are any of these wrong? The first 3 are negative and the last one's positive. This is wrong, right? So we can eliminate that one. That's wrong delta H. Cross that one out. Delta E is equal to Q plus W. Is Q plus W equal to minus 3? No, because it's these two numbers added together, right? So it can't be that one, because that's saying that delta E is equal to W. And then the difference here is that one of these, we're looking at the difference, and the other, we're actually adding the two negative numbers, right? So this negative plus this negative would get us this one. Yes? Yeah. With enthalpy, we are kind of narrowing our focus, and we're defining it in a way that the work doesn't matter. But yeah, the work is still being done, but we're not concerned about it. Yeah. Anybody else have questions? Answer is C. So the signs for delta H and delta E follow the same conventions. If delta H is positive, heat's being absorbed by the system. Heat is coming into the system. This is endothermic. The prefix endo is kind of like into, right? If delta H is negative, heat's being released by the system. It's going away. It's exiting So this is an exothermic reaction. Exo like exit. Okay? So when we talk about exothermic and endothermic, to get this correct, you have to think about, okay, if I am the system, if I am the reaction, is the heat leaving me or coming in? And that tells me whether it's exothermic or endothermic. So we started this chapter talking about the little hand warmers. There are also little packets that when you do something to them, they will become cold all by themselves. It's kind of magical, isn't it? So these chemical cold packs, these instant ice packs, we sometimes keep these, at athletic events, so, you don't have ice present. You just open this up and squish it, and it gets cold, and you can ice your sore muscle. Most of these contain ammonium nitrate, and when it dissolves in water, before the packet is activated, the ammonium nitrate and the water are separated. And when you squish it and break that internal seal, they're allowed to mix. And the process of it dissolving in water is an endothermic process. Heat goes into the reaction. Where does the heat come from? The surroundings. So if you make your arm the surroundings, then the reaction is going to pull heat from your arm, and the result is that your arm gets cold, right? And that can help reduce inflammation. The chemical hand warmers are exothermic reactions. The iron reacts with oxygen, and it releases energy. Exothermic, the energy goes out. It goes out from the system into the surroundings. Your hands are the surroundings. Your hands get warm. Okay? Burning natural gas is another exothermic reaction. Gas stove. Why do we turn it on and burn the gas? To make things cold? No, to make things hot, right? Because when you burn stuff, it releases heat. It's exothermic. Yeah.
So for the first reaction, so it needs to take energy from surroundings to make that
Happen.
reaction.
Mm-hmm. Yeah, and endothermic processes, when you think about them, can really start to freak you out a little bit. Like, what's happening is it's pulling energy from the surroundings, and that energy has to go somewhere, right? Where does it go? It gets stored as chemical potential energy inside the products. So the products of that process are higher in internal energy than the reactants were. And they got that way by pulling heat energy in from the surroundings. It's awesome and mystifying at the same time. So this is something that you need to be able to do for an exam. Identify a process as endothermic or exothermic. Indicate the sign of delta H. This can be a little bit tricky, okay? So you need to make sure you're correctly identifying the system. And then sometimes it's a bit confusing of whether we're going in or out with the energy. Sometimes it's helpful to look at the opposite to figure it out. So if we think about an ice cube melting, what's the system here? The ice cube. Nothing else is mentioned, right? The ice cube is melting. How do we make an ice cube melt? You put heat into it, right? So if I'm putting heat into it to make it melt, is it endothermic or exothermic? Endothermic. Heat is going in. So this is endothermic. And is delta H positive or negative? I am the ice cube, and energy is coming in. It's positive.
Isn't like the ice cube melting, like the ice cube's like losing energy, so it's releasing?
No, it isn't actually. Because what happens to your hand when you hold an ice cube? Does it get hot? It gets cold, right? If it was releasing energy, it would make your hand hot. Yeah. So we have to be careful when we think of hot and cold. I mean, we think about a combustion reaction is hot, right? Well, is the reaction itself hot? What we're detecting is an increase in temperature of the surroundings, right? It's releasing heat into the surroundings. We can't take the temperature of the thing burning because it's like teeny tiny particles too small to see, right? But we can observe what happens to the air around the combustion. The air around the combustion is getting hot because the combustion is losing energy. Any other questions about A? These can be confusing. Nail polish remover quickly evaporating after it's accidentally spilled on the skin. Ooh, it's cold. Acetone. I just sprayed acetone on my hand. Anybody want to try? Ugh, it smells. So what I'm observing when I spilled that on my hand got cold. It's like when you go to the doctor and they wipe your arm with alcohol before they give you an immunization. Ooh, it's cold. Did they have that alcohol wipe in the refrigerator to keep it cold? No, it was at room temperature. The alcohol on your skin evaporates. That's a process. So before we say endo or exothermic, we have to decide what is this statement suggesting that the process is. Is it the nail polish remover evaporating it, or is it my experience with my skin? It's the nail polish remover. So the nail polish remover is evaporating. That's the system. My skin is part of the surroundings. So I have direct information about what happened to my skin. My skin got cold. If my skin got cold, does that mean it gained heat or lost heat? It lost heat. If my skin lost heat, where did it go? The nail polish remover took it as it evaporated. So for the nail polish remover, this is endothermic. The nail polish remover took heat from my hand. That's why my hand got cold. So delta H is greater than 0. It's positive. Gasoline burning in the cylinder of an automobile engine. Like, well, I've never directly observed that. No, you haven't. Because it doesn't happen when you cut the engine open. But what do we know about stuff burning? It loses heat. It gives heat off to the surroundings. The surroundings can get extremely hot, right? So the gasoline is burning. Is it releasing heat into the surroundings, or is it taking it in? Is releasing. So this is an exothermic process, and delta H then is less than 0. It's negative. Because for the system, the energy's leaving. Money's leaving my wallet. You know, and online banking and cell phones and stuff are really super convenient and all, but I have 2 teenagers, and they have checking accounts with debit cards, and they text me, "Mom, can I have money for gas?" And unfortunately, or fortunately, I have the ability to open the Bank of America app and instantly move money into their account. And so the consequence is that this is like, all the time, money here, money there. I'm just like throwing money to the wind, right? It's negative. Yeah, I know, yeah. It's like, can we get in there somehow? No. So let's look at this on a molecular view. An exothermic reaction gives off thermal energy. So that gasoline is burning. The natural gas in the stove is burning. It's releasing heat. Where does the heat come from? It has to come from somewhere, right? There's kinetic energy and there's potential energy. And the internal energy of a system is the sum of the kinetic energy and the potential energy. The kinetic energy cannot be the source of this heat that's being given off because then the system would be losing kinetic energy and would be getting cold. The temperature would be getting cold. And that's not what happens, it's hot. So what's going on here is as the atoms rearrange in the chemical reaction, because that's what a chemical reaction is, you're taking atoms that were in these molecules and you're pulling them apart and you're putting them together in a different way. Their potential energy that was stored in the bonds and the positions of the nuclei and the electrons gets converted into thermal energy. So what happens is that weak bonds are broken. It takes a small amount of energy to break those weak bonds. But when a strong bond forms, it releases a lot of energy. So we're breaking weak bonds, making strong bonds, and the net result is that energy is released from the system. That's for an exothermic reaction. In an endothermic reaction, what's happening is that strong bonds are being broken and weak bonds are being formed. So it's absorbing energy to break the strong bonds, and it's only releasing a little bit to form the weak bonds. This is a good explanation, but it doesn't really help me to understand it very well. So there it is. An endothermic reaction occurs in a flask. What happens to the temperature of the flask? Well, first of all, what's the system? What's the surroundings? We have the flask, and what else is going on here? The reaction, right? So the reaction is endothermic. So is the reaction absorbing energy, heat energy, or releasing it? It's absorbing it. The reaction is endothermic. Energy is going into the reaction. Where does that energy come from? The surroundings, the flask. So the temperature is going to fall. So that the flask gives energy in the form of heat to the reaction, and that causes the temperature of the flask to go down. Any questions? Yes. Mm-hmm. Yeah, see, that's what's kind of confusing, because we talk about potential energy being stored in there, and yet those are the ones that have weak bonds. It kind of seems opposite, doesn't it? So it's not that the weak bonds are really storing energy, but they have the potential to form strong bonds. And when that happens, it releases energy. So it's hard to think about. So I guess, as I'm talking through it, I guess you could say that there is energy stored in weak bonds. But I kind of don't really like that explanation. But I think that's what it is. Yeah. Any other questions? So, talking about energy changes in reactions, right? So, we can do stoichiometry with energy. Stoichiometry is not going away. It's just going to keep coming back and back and back. Dimensional analysis. So, the enthalpy change for a chemical reaction, delta H for the reaction, is also called the enthalpy of reaction or the heat of reaction. So, there's a difference between heat and enthalpy and internal energy. For the most part in this class, if you muddle them all together, it's really not going to make a difference. This enthalpy or heat of reaction is an extensive property. It doesn't depend on how the reaction occurred. It just depends on where it started, where it ended up with. And so the heat transfer depends on the amounts of reactants that actually react. More reactant, more energy change, more enthalpy change. So by convention, tradition, we calculate the heat of reaction for the number of moles of reactants in the reaction as written. So we can look at the combustion of propane. If we interpret this equation in moles, 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. In that process, 2,044 kilojoules are released. This happens when 1 mole of propane burns. But if I wanted to relate it to oxygen, it would be this much for 5 moles of oxygen. So we write delta H over here as just kilojoules. But that amount of energy depends on how much stuff is burning, right? We don't write per mole because per mole of which thing? It's going to be different per mole of each thing. It's per amount in the equation. And so we can use this as a conversion factor to convert between moles of a substance and kilojoules of energy exchanged. Consider the following thermochemical equation. Thermochemical, it's a chemical equation, but it gives information about heat. We have 2 atoms of A reacting, and they form, I guess, a molecule. I don't know why they didn't make that A2, but whatever. Right? So this is happening. 2 moles of this would make 1 mole of that, and delta H here is negative 51 joules. So we can interpret that delta H reaction is negative 51.0 joules per 2 moles. I guess I should, that's per 2 moles of A, or negative 51.0 joules per 1 mole of AA. I take this number and I can relate it to anything in the in the equation, and the coefficient is the number of moles. It's convention. So if I'm reacting 6 moles of A, 6 moles of A, well, this is 2 moles of A. 6 moles of A would be 3 times more, right? So it would be 3 times as much energy. Which of those looks like 3 times as much? C. We could do the calculation, but it's multiple choice, and we can eyeball it, right? If this was 50, 3 50s, 50 and 50 is 100, and another 50 is 150. Okay? Because we're doing 6 moles of this, 3 times as much as indicated. So it's negative 153 joules. This was negative. Any questions? Ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So this is the amount of heat released, it's negative, for 4 moles of ammonia, 5 moles of oxygen, 4 moles of no, 6 moles of water. The amount of heat released depends on how much stuff reacts. Well, how much stuff is reacting here? Is it 4 moles of ammonia in this particular example? No, it's 155 grams of ammonia. So this is a stoichiometry problem. I have 155 grams of ammonia. And I want the heat in kilojoules. So this is kind of a heat term. So over here, question mark, kilojoules.
What is it, enthalpy?
It's the change in enthalpy, or the heat of reaction.
So what is that? Which like molecule or compound is that associated with?
It's associated with the entire reaction. All of these things, 4 moles of this and 5 moles of this, combine together, and they make 4 moles of this and 6 moles of that as a result. And when that process with those amounts occurs, 906 kilojoules are released from the reaction into the surroundings. So I have a chemical reaction and I have amounts of stuff. Stoichiometry. So what is our mantra for stoichiometry? Grams to moles to moles to grams, right? That's where we start. And sometimes that's good, and other times we need to adjust this. Are we starting with a mass of a substance? Yes, we are. Are we trying to find a mass of a substance? No. We're trying to find kilojoules. Well, I've got moles of ammonia. I have grams of ammonia, and I'm going to go to moles of ammonia. Do I need to go to moles of one of these products? No, I don't, because this is telling me that I have negative 906 kilojoules per 4 moles of ammonia. How it's conventionally written, we can apply this to any of these. So we don't need this second mole term. We don't need to go to grams, so we can go directly to kilojoules. So these end up being a little shorter. So I'm going to start with my grams of ammonia, and I'm going to convert to moles of ammonia. And I've got grams of ammonia down there. So those units cancel out. And then I'm going to use that heat of reaction term. It says negative 906 kilojoules for every 4 moles of ammonia. And so moles of ammonia cancel out. I need the molar mass of, what is that guy? Ammonia. 17.034. So I do the math, 155 divided by 17.034 times negative 906. I often forget this number in the denominator. Divided by 4, and I come up with negative 2061, should have 3 sig figs, 0.0 kilojoules. What am I going to round that to? Negative 2060, because it's 2061. If I'm rounding to the nearest tens, it's 2060, or 2.06 times 10 to the third kilojoules. Now this is another unfortunate thing with the negative signs, but it's what happens with money, and so we should be able to deal with it. If I went to the mall and I spent $100, would I say I spent negative $100? No, I'd say I spent $100. Does that mean that I've got $100 more in my wallet? No, it still means that $100 left. I'm not going to use the negative sign because the word spent indicates the direction, right? So here it says calculate the heat associated with. Does that indicate direction? It doesn't. But sometimes it'll say, calculate the heat emitted by this reaction. So then it's like spending money at the mall. I don't spend negative money. And so then we express the answer without the sign. And I will not intentionally try to trick you with this, but it is a little tricky. So in this case, we do need the negative sign. And our best answer would be this guy right here. The energy associated is negative 2.06 times 10 to the third kilojoules. The energy is leaving. It's an exothermic reaction. Any questions? No, we do need to use the negative. Mm-hmm.
What was the other term if we don't use it?
If heat was emitted or absorbed, left, gained, if there's a word that tells which direction the energy is going, then we don't use the sign.
Unless it's associated, then we do it.
Yeah, if the word, calculate the heat change when this reaction occurs. Well, that doesn't express which direction the heat's going, so then we need to indicate the sign. So like I said, it can be a little tricky, but, I won't ambush you with an exam question specifically aimed to see if you know that. Whoops. There, let's do it without the answer showing. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? And what mass of CO2 is produced? Well, again, we have a chemical reaction occurring and we have energy being transferred. It's a stoichiometry problem. This time, they're saying the 1.5 times 10 to the third kilojoules of energy produced, so that's going to be negative, right? And we want to know how much butane would we need, so how many grams of butane, and what mass of CO2, but that's the second part, we'll do that next. I know, 13 halves. What's up with that? Is this an ideally balanced chemical equation? No. Is it balanced? Yes. But if this was you balancing an equation on an exam, what should you do? You should multiply everything by 2, right? Well, if you multiply everything by 2, then you have to multiply this by 2. And by convention, we use this number associated with the coefficients in the equation. So even though it's not smallest whole number coefficients, it still works. And so we could make it harder by doing the math to multiply everything, or we could just use it the way it is. So that's what we're going to do. So thinking about stoichiometry, grams to moles to grams. Well, the beginning's kind of messy, but the end, I want grams, right? I want grams of butane, C4H10. And so I need to get to moles of butane. But what I have information about is the energy, which doesn't fit with grams or moles. So I'm just going to go kilojoules directly to moles. It's kind of backwards of the previous problem. Bless you. So I have 1.5 times 10 to the third kilojoules of heat. The negative signs are confusing in this one because this is given as a positive number, right? It's producing this much heat. So if I think about it hard enough, I realize, yeah, it's actually a negative. So let's go with that, negative. And then I want to convert this to moles of butane. So kilojoules down here. And then I want to go to grams. So those guys cancel. So this is telling me negative 2658 kilojoules for 1 mole. So if I had 1 mole, it would release this much. And then I need the molar mass of butane. So 4 times 12.01 plus 10 times 1.008, 58.12.
So if we were looking, for example, at the mass that oxygen produced, it would use 13/2 moles over negative 200.
Yeah, you'd use the fraction 13/2, which might be easier to look at as 6.5. Yeah, 6.5.
But the negative 2068 could apply to any individual.
Yes. So negative 1.5 EE3 divided by negative 2658 times 58.12. Oops. Lost a digit. 2. I'm getting 32.799, and then I'm like, oh wait, sig figs? Oh, 2 sig figs. Grams. So 33 grams of butane. If I remember correctly, this is the first time doing this problem in lecture that it occurred to me to write this as a negative number. And so the signs worked out. Usually I start with this 1.5 times 10 to the third, and we end up with a negative mass. And then it's like, wait, could we have a negative mass? Negative mass isn't possible. Well, this is the amount of heat being produced. And so I could think of that as, if I'm producing this much heat and producing this much heat, I could make all of those positive. The mass has to be positive at the end, right? So we can be real careful with our negative signs and put the negative here, and then it gets rid of this negative. Or if we're a little sloppy and we come up with negative mass and we look at the problem and there doesn't really seem to be anything wrong, we can say, well, I must have been sloppy with my negative signs and this has to be positive. What mass of CO2 is produced? Well, I could take my grams of butane to moles of butane to grams of CO2 to moles of CO2. That would work. But we're practicing with the energy business, so I'm not going to do that. We can use the same beginning of this equation. It's producing that much energy. But now I'm going to look at how many moles of CO2 are associated with this. 2658 kilojoules. How many moles of CO2 are produced for this amount of energy? 4, right? 4 moles of CO2. And then if I want grams, mass, I need the molar mass. So negative 1.5 EE3 times 4 divided by negative 2658 times 44.01 equals 99.34 grams, 99 grams of CO2 produced. questions? $33.99.